because the name tend to polarize. They touch me in positive or negative, whatever. I am from Regione Marche, so I am not from Florence, and other important things to say here in Pisa. Okay. What I am the Director of Technology Innovation University Research of IBM Italy. Therefore, I will provide a brief context of what IBM Italy is doing in this space, and after Ivano will tell what we are doing with IBM Global into this area. We have created, by the way, a new unit we call RMB, Rhythm and Blues, or Research and Business. And the joke comes from the fact, and this is important for you here in Normale, this explains an important topics, that there is not anymore much time between the research and the business itself. The development cycle has shortened up a lot. Therefore, it happens more and more that research people get directly problem from the final clients and they commute into solution. And that's an important point. Now, the organization, yes, we follow all the Italian clients, and we have this unit called Research and Business. You know, for the young people in the room, do you know what was the first product of IBM 107 years ago? It was a salami slicer. If you go, it's true. If you go in Almaden, close to San Francisco, in the cafeteria you find one. We were producing salami slicer, electric one, yes. After 1 year, we bought the CTR, computing tabulating record, and the Hollerith tabulating machine, and that's the starting of IT. That's the new IT. We are the history of IT of the last century, but we started with salami slicer. And why a company producing salami slicer after 107 years produce quantum computer? Actually, we started 30 years ago. He will tell us with Charlie Bennett and other people in that space. But in any case, why a company is now moving from salami slicer, sorry for joking, into what we are doing now? How can a company do it? It does this investing $6 billion a year in research and development. $6 billion a year for our Italian friends here in the room is, I was telling this also to the governor of the Bank of Italy, that was telling Italy is, yes, it's a problem of innovation. Yes, of course, if you don't put money, it's very difficult to. Italy is investing 20, public and private. IBM is investing 6. Only IBM. That's the problem for Italy, not for IBM. But it's not enough. It's not absolutely enough. It used to be, we used to have research in our own lab by ourselves. It's not true. Okay, of course, we cooperate, but we used to do ourselves. Not true anymore. We need to do together with our university, with the best university of the world, like you are, with the best systems, because we have this motto in research: the world is our lab. Research, IBM research is now working, and not only IBM research, IBM is working in open innovation or network innovation mode. That's why it's so important for us to be here with you. That's why it's so important to connect our research lab all over the world. The closest one is Zurich and Haifa, the one in Israel, and we have Yorktown, and we have Alman, and we have to our clients. But another important things we have, and a dream we share with our head of research in Europe, it is Alessandro Curioni, by the way, is an Italian, is from Normale di Pisa. That's good to know. That's for you that are here. Is that we want to open research lab in Italy. I mean, that's my dream. I used to say on my burial site, I want written, he opened research in Italy and he died. Now, cross fingers, probably because I will be 90 years old, things like that. As a matter of fact, at the moment we can write, he opened research in Italy, dot. Because I'm not going to die, crossing at least not immediately, but in Bologna we have received the first money from IBM Corporation and the first money from the local government, and we started with 28 people there, and I want to put some more all over the country, because I don't believe, that's another design point, we don't believe in a place like Italy you can do a single center in a single big city, simply because it's not coherent with the system of the country. So we want to spread, of course, well connected, tightly connected, but we want to distribute. We are envisioning a distributed model. We have decided 4 areas to work on. Health and nutrition, that of course is clear. You may imagine why in Italy we qualify for that topic. My daughter, when we were living in Dubai, was asking me, Daddy, how do you say pasta and pizza in English? Pasta and pizza. This, we are superpower. The second is a human-assisted solution. The third is proactive cyber intelligence and security. The fourth is new energy. In the last 3 years, we have selected clients all over the country, and with them we started to make activities. We have a client in the health space, we have client in the university space, we have oil companies, we have cybersecurity, and we have decided, and here I'm coming to the point, on foundational technology, what we call foundational technology. We have decided some activities. For example, with Vodafone, we are doing 5G experimentation for the country in Milan. And we developed in Italy the crypto card for all the world. All the cryptography card developed there. Quantum computing, we definitely want to invest. That's why we are here. That's why Ivano is here. We will tell you. He will tell you what it is about, but it's our mandate to invest there. We sent over people all over our lab and of the world because we need antennas. And to close, of course, we work with all the universities of the country. To close, even this is not enough. Even this is not enough. We believe that cooperating with the clients, what is our lab? So we have to cooperate with the research center of the clients. We have to cooperate with the research center of the country. We have to cooperate with the research center of the world. And this happened with the Italian Association of North American Foundation of Italian Scientists, ISNAF, and I started 3 years ago as a joke, and after I started to work with them, and there are Nobel Prize there, and they put me in the board of directors, and I found it very useful for retrieving money to bring to the country with the alumni. We were joking, we will tell later how we can do this. And after that, China is investing heavily in quantum, and you will see, and I moved into the Italian Association of Scientists in China to have the embassy, and after we do Israel, we are doing now Africa, because there are good movement there this was part, when I was in emerging market, this was part of my territory, and I believe there is a lot to do. And that's, we want to expand what we are doing in this country in terms of research, we want to make all over the world. That's, I am so happy to be here with you in Normale di Pisa. That's, by the way, is where is a point of excellence. You don't need any special flag for doing that. You are by design one point of excellence, and that's why we want to find a good way to cooperate with you. We believe that quantum computer is the area, and I leave the word to my friend Ivano Tavernelli, with an Italian last name, with an Italian origin, but is from Lugano. That for me is north of Italy, isn't it? Canton Ticino. Ticino is an Italian river, isn't it?
Yeah, okay. So we have to switch.
Yes, you have to change the presentation.
Yeah.
Sorry. I am ciecato. You say ciecato in...
Yeah, I understand. Yes.
Understand ciecato. And
Definitely. Super.
Can the operator switch?
No. Sì. Ah, ok. Okay. Super. So, good afternoon, everybody. Can you hear me? It's okay? And now, also? I prefer to stand, is okay? Okay. Yeah, perfect. Thanks. Okay, so I will talk about quantum computing and IBM, even though the topic is more general than what it seems, because I'm talking essentially about quantum computing in general, and then I will show to you some applications that are related to the platform that we have developed at IBM, and then you can also use through the cloud, so the quantum experience machine. So Here is the IBM research in Zurich that was introduced before. So it was established in 56, and its main focus is on, I have to read there because its focus in science and technology, system research, and computer science. So it has quite an attractive curriculum with 2 Nobel Prizes. And recently we also opened, together with ETH, a nanotech center that is run again in collaboration with ETH, on nanotechnologies. And we have collaborations with many universities, including a university in Italy. And we also contribute to teaching, so to dissemination, especially in quantum information. We started courses at the University of Zurich and also at ETH, where we try to get a new researcher into the field. Good, so this is the campus. You see it on the right-hand side, close to the Lake of Zurich. This is the outline of my talk. So I will briefly introduce quantum computing. So, I mean, the level would be what I think is medium. I will not enter too much in the details, with the risk that sometimes I will probably oversimplify some concepts. But this is, the thing to do when you have such a broad audience in front of you. Then I will introduce the hardware, and obviously focusing mainly on the hardware of IBM, because it's the one that I know the best, not because the other one are not good. And then I will move more into the theory, explaining the logic, the quantum logic, the gates, how a quantum computer operates. And the last part of the talk will be about applications, and my focus will be today on quantum chemistry, because it's where we have, let's say, the most interesting results at the moment. But if I have time, I will also show to you some other applications. So why do we need quantum computing? I think everybody here is familiar to Moore's law and the fact that the CMOS has reached the limit. And indeed, if you look in this picture, you see that there is a saturation of the performance of the classical computers. And therefore, we have to think as a society, but also as an industry, about what comes next. So what are the next strategies possible? And one of those would be to use 3D architecture, so move from 2D devices to 3D, with all the problems that comes with this type of fabrication, like heat dissipation and so forth. The other option, where also IBM is very active, is on neuromorphic or cognitive type of computing. And the last one, the most recent one, is quantum computing, which is the subject of this talk. Quantum computing is a very broad concept. Indeed, we talk about a quantum ecosystem, right? Because you need many components, ranging from, obviously, quantum computers you will see in a few minutes, they operate at 20 millikelvin, so you need a fridge that can cool down your device at 20 millikelvin. Then you need also to design the qubits. And to do that, you need simulators, so you need possibility to simulate your quantum device. And to do that, you need large computers. So in order to simulate 50 qubits, you need a very large HPC. And if you want to simulate, say, 100 qubits, there is no way you can do it on Earth. And next, you need also to connect, eventually in the future, these quantum computers together. Already the quantum experience is available on the cloud. You need fabrication. That's also very important. You need control software, because, again, the electronics has also to function at 20 millikelvin, so this is a challenge for microelectronics. You need quantum algorithms, and this, I will convince you, that is a real challenge for the future. And the reason is because you cannot take a classical algorithm that you have developed or somebody else has developed to solve, for instance, electronic structure problems in this case. You cannot simply translate those into the language of quantum device, but you have to start from scratch, right? And this is what we are trying to do now at IBM, but in other many research groups together. Then you also need simulations to do system characterization. So you have these new devices that are built. You need to be able to characterize them in order to be able to improve them. We will see soon that the quantum devices are not yet perfect or like we would like to be them to be because, for instance, we have decoherence times in the order of microseconds, and this limits the performance of these machines, and therefore we have really to try to characterize them better in order to improve fabrication and get better performing devices. So these slides clarifies a bit the state of the art, right? On the left-hand side, you have classical computers in the 1940s, and you see that probably this machine has now the power of your mobile phone, and it was that large and very difficult to operate. And what you have on the right-hand side is a quantum computer in 2010. So this is the analogy. So we are really at the beginning. There is a long way to go, same that we experienced with classical computers, that you see that the kind of evolution we had in the last decades. So a lot of work to do for the young generations. Why quantum computing? So we know that there are many problems that are hard to solve using classical algorithm and classical hardware. One of the problems that probably is more popular is the factorization of large numbers that is using cryptography. But there are many challenges also in algebra to solve a very large system of linear system of equations that can be used, for instance, in finite element modeling, and also in the combinatorial optimization and in the simulations of quantum mechanics, right? So quantum mechanics is still a challenge today because of the exponential scaling of the resources that you need in order to solve the Schrödinger equation for a system of n electrons, right? And this is important in chemistry, but not only, also in material science, drug design, and all that. I mean, there is really the need to have better performing algorithm to solve the Schrödinger equation for material science. Good, so the aim of everybody is to get to the fault-tolerant universal quantum computing. So this is our goal, probably not in the next 10 years, but we are working hard in that direction, right? With such a machine, you can essentially perform any calculations, hopefully with polynomial scaling, right? The problem is that in order to get there, you need error corrections. And in order to get error corrections, you need an overhead of physical qubits. Because in a way, the way we see it now is that you need roughly 1,000 physical qubits to get a single logical qubit that you can operate. So it's really something for the future, and is our goal because this machine can solve essentially any problem you can think about. On the other extreme, what we have now, we have large quantum machines that function as annealer, right? In this case, you can treat a small class of problems for which you are looking at the minimum of a cost function that can be the Hamiltonian of your system, meaning that you are looking for the minimum in the energy, without getting trapped into local minima that are hard to overcome using classical algorithm, right? And this is, for instance, what D-Wave is doing. They have thousands of these qubits, and the machine is highly specialized to solve these kind of problems, with many drawbacks, right? Because usually they show you a landscape like this one, so the ground state potential energy surface, but they don't show you the excited state's potential energy surface. And you know that when you drive the system along this potential energy surface adiabatically, right, you are never slow enough to guarantee that you don't excite the system into the excited states. So there are really very big limitations. Anyway, it's not a universal quantum computer can only solve a small class of systems. So IBM instead took another path that is probably more ambitious, to start with very small devices. At the moment, we have on the cloud system 5 and 16 qubits working. But this type of device are the first step to move to the right column, so moving towards the fault-tolerant universal quantum computer. So they are the building blocks for the future universal quantum computers. At the moment, we are working on algorithm that can already prove some quantum advantage with approximate quantum computing. So with this type of not yet fault-tolerant machines, we can still produce algorithms that can show quantum advantage and therefore can become useful in many applications ranging from material design, quantum chemistry, optimization, and machine learning techniques. So here is where we stand. Let's move now to the most technical part that introduces the logic and the gates in quantum computing. So I start really very basics, showing you a single bit on the top and, on the left-hand side that can take only the value 0 and 1. Right? A qubit instead, as you know very well, can take any value between 0 and 1. And since we are dealing with complex amplitudes, then these superpositions are described by a vector on a sphere that we call the block sphere. So with the two angles theta and phi, you can describe any linear combination of the two fundamental bits, 0 and 1. So this is already, you see, the change in paradigm. Before you had 0 and 1, now you have an infinite number of values possible between the state 0 and the state 1. Now, a classical device, if you set it at 0 and you measure 0. If you set it at 1 and you measure, you will get 1. A quantum device, if you have the state in 0 and you measure it, you get 0. If you have it in 1, you measure it, it's 1. Right? And if you repeat the same simulation many times, you get exactly the same statistic. Nothing is special if you have a pure state, so an exact state 0 or 1. Now, instead, if you build a linear combination with equal weights of 0 and 1, this is not normalized, but it doesn't matter, then if you start measuring this state, then you see that you can have 0 or 1, depending how this state will project back to the direction where you operate the measurement that is the vertical axis on the block sphere. And if you collect the statistics, you recover that the system is 50% in the state 0 and 50% in the state 1. Okay, if you change now the orientation of your vector in the block sphere, you repeat the experiment, you collect statistics, you get 64% in 0 and 36% in 1. So far, I think everything is clear. And what is that? I mean, is quantum mechanics just statistical mechanics? So I can build a classical machine that can exactly reproduce this type of information? The answer is obviously not. And the reason is that it was because I was asking the wrong question. I don't have to ask what is the probability that is 0 or the probability that is in 1. What I have to ask is what is the probability that I have at the same time 0 and 1. And this, the probability to be in this state is 1. I measure it 100 times, I still get 1. Okay? So this is the big difference between statistics and quantum mechanics. Classically, in order to get this combination, you will have to sample the 0, 50% you will have 0, 50% you will have 1. And then, again, statistically, you will have 50% of the two states. Quantum mechanically, with a single measurement, I can spot 100% this state. Okay, so in summary, so when we are treating superpositions of states, this is the way we call 0 plus 1 in quantum mechanics, then we are not measuring a statistical mixture of 0 and 1s, but we are measuring a quantum state that is called a superposition state. And in the common language, probably everybody here is familiar with the Schrödinger cat, that the Schrödinger cat is dead and alive at the same time, right?
What about Schrödinger?
Schrödinger is dead. So far. But the cat lives longer. Okay, another important ingredient of quantum computing, in addition to the superposition principle, is quantum entanglement. Right, here is a bit more complicated concept. I try to really simplify to the minimum. You have in the picture there, you have, say, a singlet state in an atom, so two electrons with the spin that is pointing in opposite direction, up and down, alpha, beta, depending how you want to call it. And then when you bring them apart, you separate them, even very far from each other, then quantum mechanically the two objects remain in a way in communication. So if I do a perturbation, a system on the right-hand side, then this has an influence on the system on the right-hand side. And this is, again, something that is only valid quantum mechanically. So if you do a single measurement, classical and quantum theory predicts the same, but if you compute correlation functions of this experiment, then you will get what are called Bell's inequalities that will tell you that what you observe cannot be replicated with a classical theory, but is really a quantum phenomenon, right? And this philosophically have many implications. So there is the Einstein-Podolsky-Rosen paradox, for instance, that is very much related to this property. Very important is the non-locality of quantum mechanics. The fact that when you split these two particles, they still communicate even when they are very far apart, is something that, is classically impossible, right? If you, from Newton physics, we know that interactions should be local. So, and this quantum mechanics is completely non-local. And there is no way to complement quantum mechanics with hidden variables to make it a classical theory. This was proven already by von Neumann and other people. But for us, what is more important is the last point that you have here. Is that thanks to the entanglement, we can build a huge Hilbert space starting from the fundamental block of a single qubit. Right? The space that n qubits can span is 2 to the n, meaning that every time I add a single qubit, I double the power or the size of the Hilbert space, and so the power of the quantum machine. Good. So this is a chart that makes this concept probably clearer. So if I have a single qubit, then the amount of information that I can store in a single qubit, since it has two states only, then is 16 bytes. If I have 2 qubits, then the theoretical number is 4, right? 2 to the 2 is the 2 to the n power law that I mentioned in the previous slide. If you have 8 qubits, then you have 256 states that corresponds to about 2 kilobytes. Now let's move to 64. If you have 64 qubits, then what you can store in your quantum machine, ideally, is the information that you have in the internet nowadays. You only need 64 qubits for storing all that amount of information that corresponds to 74 millions of gigabytes. And the time that a classical computer we need to operate with all this amount of information is equivalent to years on a supercomputer. Now, if you move to 256 qubits, then the size of the Hilbert space corresponds to the number of atoms in the universe. And obviously, you will never be able, using HPC, classical computer, to deal with such an amount of information. So, and we are only at 256 qubits, right? But these have to be good qubits, with all possible entanglements and without errors and other things that I will show in a moment. But the power, theoretical, is there. And this is why many companies decided to invest in these techniques, and also many universities, because the potential of this type of machines is enormous. Now, this is about the fundamentals of quantum mechanics that is needed in order to understand the logic of a quantum computer. So I repeat, is the superposition of states, the Schrödinger cat, plus entanglement that allow us to enlarge the Hilbert space in order to have something where to store a large amount of information and then try to use them in the most convenient way. So now I move to the fundamental units, the gates. That is a way to translate this concept in quantum mechanics on a real hardware in order that you can use it to build quantum algorithms. The first one are the single qubits operations. So here we put the state 0 on the north pole of the block sphere and the state 1 on the south pole. And as I mentioned before, you can generate in a quantum computer any linear combination of these two states. To do that, you need two angles, the Eulerian angles, and you have to guarantee that the total norm is 1. And here you have the representation of the state psi, that is 0.250, plus a complex number time 1, meaning that 90% of the time will be measured in 0 and the rest in 1. So that's basic quantum mechanics. And now you have the gates that operates on this qubit state. Now we can map the state 0 into 0, 1 with some coordinates 1 and 0. And we map the state 1 with, say, Cartesian coordinates 0 and 1. And at that point, we can operate with matrices, right? And the first operation that I show here is the X gate that moves your qubit state from the north pole to the south pole. And the matrix representation of this operation is a 2x2 matrix and operates on your vector generating a new vector. So very simple maths. It's just linear algebra. You can have Z gates that perform the operation that you see in the second column. And you can have Hadamard. Hadamard is one of the most important gates because it produces what we saw before. It's a superposition of two states. You see that the first operations from 0 went to 0, from 1 went to 1, or there was a swap from 0 to 1, 1 to 0, but it was not creating a superposition. The Hadamard gate instead produces a superposition of the two states. So you end up 1 over square root of 2 of the sum or the subtraction of the two states. We build a Schrödinger cat using the Hadamard gate on a single qubit. It's really not bad. You can do more, and this is all what you need in order to write your quantum algorithm. You need also 2 qubits operation, and this is in order to entangle the systems together. The first one that I show here is called the swap gate. So it's essentially changing the 2 bits of information in the 2 qubit state. So 0, 0, you invert it, you get 0, 0. 1, 0, you get 0, 1. And the second one, that is very important because it's generated entanglement, is the so-called C0 gate. And what it does is swaps the second bit depending on the status of the first. So 0, 0, the first is 0, doesn't do anything. 0, 1, the first is 0, doesn't do anything. 1, 0, the first is 1, then it operates on the second, inverting from 0 to 1. 1, 1, again, the first is 1, then operates on the second one. And then if you want to generate what is called a Bell state, so a state that cannot be represented as a single product, but is really an entangled state, is your first entangled state that you see here. You have to operate in this way, first with the single qubit operation H, which is the Hadamard that computes the superposition of 0 and 1, and then the C0 gate that does the entanglement between the 2 qubits, and therefore you get, no, this is not the way to point, I think, wow. And therefore you get the Bell state there, right? So an entangled state made of 2 qubits that cannot be represented in a classical way. It's purely quantum mechanical. Good. Now that we have an idea what are the key elements, so we have superposition and entanglement. I try to explain you quantum mechanically. And then we move to the equivalent in the circuits. So we have the Hadamard and the C0 gate. So these are the 2 operations that can reproduce the quantum mechanical properties that we need in order to operate with a quantum computer. But this is only theory. Now we need the hardware. So we need to run this algorithm somewhere, and the hardware now is the topic of the next part. So you have different possibilities here. How much time do I have? 26 minutes. Okay. So we have different possibilities here to make a very long story short here. I will only mention the last one, that is the one that I will describe. I'm not really good in this, because also I don't see. Yeah, it would be this one, the superconducting circuits, right? And why they are so, say, powerful, and why many institutes and many also companies moved into this technology to produce quantum computers. The reason is that this superconducting qubits is a way to reproduce the properties of an atom in a very large scale system. So this is a millimeter scale device and has exactly the same property of an hydrogen atom, right? And therefore you see clearly the advantage here, because it's easy to manipulate, right? It's much easier to manipulate something that is large, bulky, than to manipulate single atoms that the day after they are not what they were the day before, right? So this is a very robust type of device, easy to control, easy to fabricate, easy to replicate, and therefore is, for the moment, the technology that is most promising, and that can be scaled up, as we saw, to thousands of qubits in the case of D-Wave, and to a couple of tens of qubits for IBM and other companies. So these are the fundamental building blocks of the superconducting qubit. There is the qubit itself that has the potential energy surface that you see on the right-hand side. So here, right? This is potential energy curve of the qubit. The circuit representation of the qubit, you have it on the left. So is a circuit with a capacitor and an inductor. And the inductor is, in this case, it's not a real inductor, it's a Josephson junction that produces the anharmonicity. And this anharmonicity of the potential is very important because we want to generate a qubit. So every time we excite this device, we want only to operate between 0 and 1. And probably here you remember from your basic quantum mechanics that if you have an harmonic oscillators, like in the picture below, so down there, wow, the delay is really, okay, it's better I don't point. So the picture below, then you see that you have an equal spacing of your energy levels. And so if you excite the system from 0 to 1, at the end you obtain the excitation of all the states. So you end up, if you absorb 2 photons, then you get to the second excited states, because you have exactly the same spacing between the levels. And this you don't want in a qubit, because in a qubit we want to operate between 0 and 1. And the way to break this symmetry is to make your potential anharmonic, and this is done by adding this element that replaces the inductor and is called the Josephson junction. And this is an element that is a superconducting unit that operates only a very low temperature, and this is also the reason, one of the reasons, why we have to cool down the device to 20 millikelvin. The other ingredient of component of your quantum processor is the microwave resonator that is used to read out the state of your qubit. It functions as a bus, so in order to induce entanglement between different qubits, and also as a noise filter. And this is purely harmonic. But there you don't store any information. So this is the circuit that represents the oscillator, the Hamiltonian. Then you put the heads when you do the quantization of this, and you get all your level equally spaced, because it's a perfect harmonic oscillator. This is the other ingredient of a quantum computer. Already is just a repetition. So this is the capacitor with the Josephson junction. So this is the Hamiltonian, and you see immediately that there is a cosinus function here. It's a function of the flux in your qubit, meaning that your potential is not anymore harmonic, but has this sinusoidal form. Therefore, he has this shape, and you get what you want. So a different energy spacing between 0, 1, and 2, and all the series of excited states. The realization of this, as I mentioned before, these are macroscopic objects, right? You see that this has a spectrum that resembles the one of the hydrogen atom, but is made of many very bulky elements in the scale of nano and millimeters. And when you have a state that is moving from 0 and 1, you don't have a single electron that is excited, but you have a number of Avogadro, of Cooper pairs that moves from one island to the other island of your circuit. So it's really a macroscopic object. So you have Cooper pairs, but really enormous amount of Cooper pairs that moves from one side to the other of the Josephson junction. Good, so far for the hardware, this I skip, and I move to this picture here where I try to summarize the different components of a quantum device. So you have on the left-hand side the electronics. In the center you have the dilution cryostat. So the upper plane is roughly 2 Kelvin, and then as you move down in this fridge, you can reach the temperature of 20 millikelvin, is where you have sitting your qubits. You have the qubit here on there, on the upper corner, that sits exactly where is the coolest part of your device. Voila. And if you use quantum experience, is on such a machine that you're performing your calculations. Good. This is the short history of IBM quantum processors, starting from 2015 with the 4-qubit device. In 16 we have the 5, so we double the performance of the machine. Remember, every time you add a single qubit, you double the performance. Which you can already see this chip as the fundamental plaquette for a surface code type of architecture. You can link them all together and scale it up. We don't do that yet. Then we have the 16 qubit in 2017 that is also available on quantum experience. I will show you later on. So you can use for free this device and do your calculations and your tests. And the 8 qubit device is also available, but I will not discuss it here. So this is the concept of quantum computer. I mentioned before that there are several types of quantum computers available. Not available. Available, there is only the IBM one, but built in a way. And you have some with many qubits and some with less qubits. Now you can tell me, but why IBM has only, say, 20 qubits while D-Wave has many, many more? And the reason is that the nature of these qubits are very different, right? And here I report a chart that measures the quantumness, so the quantum value of your quantum machine, or the quantumness of your machine as a function of the number of qubits, so which is this axis here. My God, no, okay, the axis that goes from something happened?
Nice picture, yes, of course.
So this is not in my presentation. Il salvaschermo, okay. Okay, thanks. So on the x-axis you have the number of qubits, and in the y-axis you have the error, right? Large error towards small error. So in order to have say, good performing quantum device, quantum machine, you need to have both of these properties. So you need to have many qubits, because if you have only small qubits, then you can simulate it with your mobile phone. But you also need large fidelities on your operations. So you have to be able to reproduce exactly the operations like the Hadamard gate that I was mentioning before without error. So, and in order to get a large quantum volume, you have to move essentially along the diagonal. And this is the path that IBM took. So gradually increase slowly the number of qubits, trying to improve simultaneously the coherence and the fidelity of your qubit operations so that you can maximize the quantum volume. As I mentioned, there are other strategies. Other companies took another path. They first increased the number of qubits, but without showing any quantum advantage, because you see that if you move from 5 to 500 qubits with small fidelities, your quantum volume doesn't increase. And then later on, they claim they will move on the other direction and reach high quantum volume. IBM now sits roughly in this position here. Good. Now, let's have a look to the software. So, as I mentioned already a couple of times, we have a web platform on the web so that you can access through the cloud, and it's called Quantum Experience. We have already many researchers publishing using this tool, also using this tool for teaching quantum mechanics, hopefully in the future also quantum chemistry. The nice thing is that you sit on your desk, and for instance you can in 5 minutes prove Bell's inequalities. Something that at my time, when I was a student, it was impossible even to think about, because you needed really a large lab in order to be able to perform this kind of operations. Now, really, you can prove the fundamentals of quantum chemistry, or quantum mechanics, sorry, sitting at home, maybe watching TV and at the same time proving Bell's inequality. I think is a great tool also for teaching, but now it becomes more and more an important tool also for research, because we are getting to the point with 20 and in the future 50 qubits where we can show quantum advantage with such an architecture. These are the quantum processors that are available on Quantum Experience. The original one that was released in 2017, actually in 15, so here there is a mistake in the slide, is the 5-qubit chip with the connections that are shown in the part below. So not all qubits are connected with all qubits, but with swaps gate you can also entangle any pair of qubits that you have in the chip. And in the one on the right-hand side is the 16 device, also accessible on Quantum Experience when you can perform really interesting calculations also in quantum chemistry. Good. In order to interact with these machines, we prepared a software platform which is called QuizKit that you can download also for free. It's an open source code. And then using Python scripts, you can directly interact with the machine and run your calculations directly on the quantum device or in a simulator that is also made available by IBM free of charge, and with which you can simulate up to 40 qubits, roughly. Okay, so far about the basics. Now, for the remaining 2 hours, or less, I will...
10 minutes.
10 minutes, I will try to give you a flavor of what can be done in a real application, right, in quantum chemistry. So was Feynman that introduced this field in a way, saying that, hello, I mean, nature at the fundamental level is described by quantum mechanics, and you're trying to compute it with classical machines. Maybe we can do better if we move to a quantum computer and try to simulate quantum world with a quantum machine. And we picked this challenge, and already in 2015, IBM Yorktown produced this paper that got into the cover of Nature, where they showed the first calculations on very simple molecules, and try now in the next 9 minutes to get there. So, why chemistry is a challenge? I'm sure that I don't have to explain it here. You start with the Schrödinger equation, and you have the problem that if you use a classical algorithm to solve this equation, you have an exponential scaling. I mentioned already at the very beginning. So you need an exponential amount of resources with the number of electrons in your system. Instead, the cost on a quantum computer to solve the Schrödinger equation for a system of n electrons only scales n to the power of 4. So it's a polynomial scaling compared to an exponential scaling. So there is a potential benefit there. this I skip it, and just mention to you that obviously also in this school, I mean, there was a lot going on in quantum chemistry and the simulation of computational quantum chemistry. So people were not waiting for the quantum computer, but making approximations on the Schrödinger equation that were able to describe very large systems, right? Starting from Hartree-Fock, going to all post-Hartree-Fock methods. The only thing that I want to show you here is that if you want to improve accuracy, moving from the left to the right, then the cost of your algorithms increases dramatically. And therefore, for instance, at the level of CCS-DT, coupled cluster, single, double, and triples, you can only treat rather small systems because of the cost. And now what we want to do with a quantum computer is getting this type of accuracy, but with a much better scaling. Good. And this is the state of the art, if you want. So we simulated these molecules, but later on I will show that we move also to larger systems. At the moment, we have only few qubits. We can only do small systems. But again, every time you add a qubit, you double the performance of your machine, meaning that with a couple of hundreds of qubits, we will already be able, good qubits, we will be able to simulate systems that are already hard for a classical machine, for HPC, like this iron-sulfur cluster that have very complicated magnetization properties. Good. Let's see how we do that. So the way we solve, let me see where I stand here. Okay. So the algorithm that we use in order to solve these problems is the following here. So we take in this case, our Schrödinger equation, we map it into the qubit, and we have ways to do it automatically using the QuizKit software that I mentioned you before. You transform your fermionic Hamiltonian into a qubit Hamiltonian that you can simulate on your quantum device. You don't, it's like a black box. You don't see anything here. Just have to enter the coordinates of your system, the basis set of your system, and is translated automatically into a qubit Hamiltonian. And then this qubit Hamiltonian, then we generate on the quantum circuit a state that depends on the rotation on the block spheres that I showed you before, and also on the different gates that I use for the entanglement. This is the psi theta that is shown in the blue box. And once you prepare in your circuit this state, then you can measure all expectation values. So the quantum computer will produce all expectation values, and if you compute the expectation value of an Hamiltonian, you get the energy of the system. So now the quantum computer is able to produce you the energy of any state that you prepared and parameterized with the angle theta. This information is passed to a classical computer. Now this is the red box that minimizes the value of the energy in the space of the theta parameters. It does change in theta, gives back the value of theta to the quantum computer that re-evaluates the expectation value, so computes the energy for the new set of theta, gives it back to the classical machine that does another step in the optimization, and you continue until you iterate until convergence. And therefore this scheme is in a way a mix architecture where you need a quantum computer that performs the calculation of your matrix elements, the energy, and a classical computer that does the optimization in the parameter space. Now here I put an HPC, but you can do it with your laptop because the systems are still very small. Okay, now here a few equations and then I stop, promise. So I try now to show you quickly in 3 slides how you map a quantum chemistry problem into a circuit. First of all, you compute for instance, Hartree-Fock equation. So the Hartree-Fock equation is a simplified Schrödinger equation for a many electron system that provides you the orbitals, and the orbitals you have them on the left-hand side, right? Once you have these orbitals for a given molecule, in this case an atom, then you compute all possible integrals among those. These are the HPQ and HPQRS that you have there. All these you do it classically because you can do even a protein at this level of theory. So you compute all the orbitals that you need and all the integrals among these orbitals. You do it classically. And now you use these parameters to parameterize, also to compute the Hamiltonian. The Hamiltonian is given below, is in second quantization form, but the only thing that you have to worry here is that this Hamiltonian is parameterized as a function of HPQ and HPQRS that I computed before, right? So by doing this very simple Hartree-Fock calculation, I have all the ingredients to build the Hamiltonian. And now what we need to do is to compute the wave function. And this is the hard part. A classical computer cannot compute this wave function because it's an exponentially large problem, so it's a hard problem, and it's very time-consuming to get it with a classical algorithm. And now we see how it works in a quantum computer. Now you take all your orbitals that you generated before, and you put them on a quantum register, right? So you say that the first orbital is occupied, you put 1. The second orbital is occupied, you put 1. The third is occupied, the fourth is occupied, and then the other ones are not occupied, you put zeros. Right? You have all your qubits, and you say, this you represent the 1s, you represent the 2s, and the 2p, x, and 2py, and all the others are 0. And then you give an amplitude to this state, you call it theta 1, this amplitude. Then you add a second amplitude, that now you see that I have excited the fourth electron into the fifth electron. And in this way, I can compute the linear combination of an exponentially large space, actually combinatoric large space, and parameterized by my theta parameters. So very simple is occupation. If an electron, an orbital is occupied, I put 1. If it's not occupied, I put 0, and I do all possible occupations, keeping the number of electrons constant. Then this is my trial wave function, and you see it's parameterized by the angle theta, as I promised before. Then you take this wave function and you pass it through a circuit that I will not describe, and on the other side, it will give you the value of the energy for this trial state, parameterized by theta. And so you get energy as a function of theta that you optimize on a classical PC, giving back the values of the theta parameters that you place again in front of your quantum register, and you generate a new state parameterized on the same theta parameters, and you repeat this operation until convergence. At the end, you have the minimum energy of your system. This is the way you encode a wave function in a quantum computer, and the way you can benefit of having a quantum computer in quantum chemistry, because you can solve this exponentially hard problem in a polynomial time. Good. 2 minutes to show the example, the simple example for hydrogen. You have a theta function, the electronic wave function of the hydrogen molecule, so H2, parameterizing the angle theta, the corresponding Hamiltonian in the spin operator, so after the transformation to the qubit space, the expectation value, and the energy. Here is what you get if you use this algorithm. So depending on the circuit that you have implemented, I don't discuss the details, just look at the two curves that converges below -1 Hartree. You see that by doing this iteration, you get down to the red line, dashed line, that is the exact value for the energy of the hydrogen molecule at a distance t. So showing that this quantum algorithm with, say, something like 50 iterations in the process that I mentioned before, it can, so this process here, right? Voila. So this, you iterate below between the quantum and the classical processor until, and you do this as many times needed to get down to the exact value. And if you repeat this operation for different distances, you reproduce the dissociation curve that you have in the inside. And this has a perfect match with the experiments, with the exact results. Here is another example. For water molecule, I promise you that we can already scale a bit larger systems. Starting curve is the red curve in the energy profile for the dissociation of a proton in water. Hartree-Fock is the starting state, the red line, and then performing this type of calculations, we get close to the black line, which is the exact solution. So we can really reproduce couple cluster results now in a quantum computer. And very last is the example on the right that is of interest for the people familiar with density functional theory. So this is a chemical reaction, is the inversion of ammonia going through a structure that is planar, and this is on top of the barrier that you have on the right-hand side. If you do this calculation in a quantum computer, you get the green line that is essentially on top of the black line, which is the exact result. If you use a density functional theory with a PBE 0 functional, which is a very accurate functional, actually it's an hybrid functional, you get the blue dotted line. So now you see that a quantum computer can already outperform density functional theory for a system like that. So there is really something here that we want to push forward in order to be able now to move to larger systems and show quantum advantage in quantum chemistry. And with this, I think I conclude acknowledging all the people that are behind this work. And I thank you very much for your attention. Sorry if I was a bit long.
Thank you. I am a quantum chemist since nearly 60 years. I think that the main parameters for parameter your qubit calculation of quantum calculations is the qubit angle theta, polar angle in spherical coordinates. Here, I would like you repeat the definition in the qubit space, because it's quite difficult for me to understand better. Thank you.
Right, so. It would be better for me.
Okay, here you are.
Ah, okay. Thanks. So I go back to the initial one where I was. Okay.
Very beginning.
Very beginning. Yeah. Try to be fast.
Because it's the main parameter.
I mean, I think that here is okay, right? Yeah. So what is?
Okay. You see that. The coefficient you got the amplitude of 0, 1, etc.
Yeah. You can try any states.
Perfect. Very good.
We do an entanglement. He thinks I press.
Thanks.
We have good teamwork in IBM, by the way. It's one. Like here.
I would like to ask a question about quantum simulators. Now, you explained very nicely that you have this, let's say, synergy between your quantum computer and a classical computer that at some point takes over and does a classical simulation. Now, do you see any potential for a synergy between your quantum computer and maybe a dedicated quantum simulator that could do part of a quantum evolution, maybe specifically for one chosen problem, and then hand the answer back to the quantum computer?
Yeah, I mean, with the state-of-the-art architectures, I think that this is the only way to go for the moment. So try to think about the quantum computer as an accelerator for a classical computer. I don't know if this answers your question, right? So there is the exponential hard part of the problem that should be encoded into the quantum device. And then it's very hard to do algebra on a quantum computer with the limited resources that we have now. So resources means not only the number of qubits, but also the circuit depth, so the number of gates that you can put. And therefore, this part, everything that has to do with arithmetics, is better to do it on a classical device. And so for this intermediate period where we have only, very primitive still qubits, then this is the way I see it. So the quantum device is mainly an accelerator for, in quantum chemistry it's very clear, the difficult part is to compute the matrix elements in Hilbert space. And this you do it entirely on a quantum device. And then the optimization of the parameters in the future, probably this will also be done by a quantum device because a quantum computer is a good optimizer. But at the moment, we don't have enough qubits to do also this part, to dedicate this part to the quantum computer, and therefore we do it outside on an HPC. But this is for convenience.
Actually, could I follow this up? Because so this was very clear. Now, my question was more in the direction of a quantum simulator, like a dedicated quantum system for one specific problem that could maybe interface with the quantum computer, and then maybe, you know, so are you doing any research in that direction? Exactly, that's what I mean.
Problems to really understand the future of the quantum annealer, right? Because still the proofs that it's a quantum machine are a bit shaking, and I don't see so much quantum advantage with this type of architecture, and therefore we are not investing time on that until this gets a bit clarified.
Okay, thank you very much.
Go.
I have a question about your algorithm for solving the quantum chemistry problem. So, if I understood correctly, you need at least as many qubits as there are orbitals, right? Or basis functions. So for large molecules, let's say you have 1,000 basis functions. And then you need 1,000 qubits, which is a lot. But in the previous slide, you wrote that with 256, you had as many, you could encode as many particles in the universe. So it seems it would be overkill to have 1,000 qubits for just one molecule. So is there a problem with the algorithm that you're not?
I mean, we just started, right? So, and we design an algorithm that works and functions in this way. First of all, we use second quantization. We could stay in first quantization and discretize the space and map the Cartesian space into quantum computer. That's
Quantum Monte Carlo, for example.
I mean, it would not be quantum Monte Carlo. It would be a quantum algorithm.
So in principle, it should be possible to
it's possible.
use
I mean,
fewer.
The reason why we move in second quantization and these early stages of these developments is because it's easier with a limited number of qubits to do a calculation that is, I mean, that has some interest in quantum chemistry. I mean, even H2, if you want to simulate it in first quantization, you have to discretize the grid, the space. So you need maybe hundreds of qubits, I mean 100 qubits to describe the space of 2 electrons, right? So the entry point requires a much larger number of qubits in first quantization than in second quantization. This is why we move in second. But it's true, I mean, this is really the problem. IBM cannot do everything by themselves, so we need the help of academics to look for better algorithms. Your point is exactly that, right? So in the potential, I always talk about potential. Potentially, in 256 qubits, you can store an enormous amount of information. But this is not what happens, right? Because if a Martian comes with a quantum computer and gives it to me and say, this is the perfect machine, fault tolerant and whatever, I don't know how to use it. We have to work a lot in order to produce the algorithms that are able to profit from this potential of a quantum machine. And there is really a lot of work to do. I mean, we are just at the beginning.
Thank you.
Thanks. Well, first of all, thanks, of course, for the presentation, and we're all impressed by the fact that this does exist. Once I say this, however, this is not what Feynman had in mind, of course, because we have not seen a real fully quantum calculation today. So the question would be, I saw about 80,000 users on your platform. Among these 80,000 people, I'm sure some face different problems, not quantum chemistry related, that were treated in a fully quantum algorithm. So at what stage are we on this front, and in which fields do we see something significant happening and credible?
I had some slides on that, but so there is one part of the group is working on optimization problems using digital architecture, right? So for instance, in finance, we are preparing a paper on that. And for the solution of system of linear equations, so finite elements, sorry, it's not where I wanted to go. And we have also now a couple of projects in these topics here, like combinatoric search in the chemical space. You know that the number of structures that you can generate is enormous. Here I have an example. So on these steroid-like molecules, we have many entry points that we have a library of ligands that can match with these points. This is a combinatoric problem again, very hard to solve with a classical computer. On a quantum computer, we can load a superposition of all these combinations and then optimize a cost functions that can be the interaction of this new molecule with an enzyme pocket, and trying to minimize all these structures simultaneously and find the best match of ligands and insertion points. And the second one is the very well-known problem of protein folding on polymer folding. Also this problem, we know very well that classically you can probably fold ab initio using classical force fields. You can do it probably with 20 amino acids. Not much more, and again here potentially you can have quantum benefits. Right? So now we have a paper in preparation on this where we start like in the old times with a protein on a lattice, a 3D lattice, and we solve, we find the minimum of the potential energy of this system in the lattice. And it works. You see definitely quantum advantage, but again, we have limited resources, so we can only show the potential of the method, but we cannot go further than that at the moment. Yeah. But there are many areas that are of potential.
I have a question about the number you showed in one of your slides, which I fully don't understand where it comes from. It's the number of bits which are of normal information which is related to the number of quantum bits. I mean, when you say that a system of 2 bits is related to 16 or 32, I don't remember exactly, number of normal bits is just the dimension in normal bits of the qualification of the angle. So where does that number come from? It's the same slide that my colleague...
The number of bits and bytes that you can store in a given number of
qubits. Yeah.
This exactly the formula that gives you these numbers. I cannot recall, but this you find it in the literature.
Okay.
Yes.
Thank you.
I was curious. Has IBM sold in quantum computers at the moment? Yes. Yes, we are not selling a full quantum computer at the moment. We are selling access to the quantum computer with the number of qubits superior to the one available on the quantum experience. Why we have this? Because some clients, like big banks, for example, are asking to have an access with a couple of, with 1 qubit or 2 qubits more than the one generally available. And that's just a way also for us to test the feasibility of the market of this stuff. But of course, to be serious, my boss keep asking me, quantum and vendi, how much do you sell? Not much. We are not making money out of it. Realistically, this is still research, and this is what IBM is doing in the research space. Basically, it's not a commercial things at this stage. Of course, in some years from now, we hope to move into commercial because we are a commercial company, but by investing 6 billion in research, so we will keep having a strong research. But this is a research effort at this stage. We have this, on a commercial standpoint, that's what we have at the moment, yes. But we don't sell hardware equipment at this point of time. We don't sell a quantum computer at home, yeah.
Okay, we have here one last question, yes, and then there will be refreshments at the other end of the floor.
After I have a question for the room, after the last question.
Yeah, you focus on energy, but, you know, large community of quantum chemistry now is instead working on molecular properties, so systems evolving under the effects of external fields. How far are you from that, and is there any interest towards this direction?
Question. Indeed, I take the opportunity to say that at the end of this month, IBM will release the first open source version of the QuizKit code, or QChem library, where you can run simulations on quantum chemistry also. You can compute energy, but also properties. So we have already dipole, density, and excited states that are in it. Okay? So obviously it's not general for, I mean, doesn't yet apply to very large systems, but we are moving in that direction. Obviously, the aim is to do design and things like that. So we also have a project on alchemical potential, so to change the structures in order to fit to a given external potential and try to optimize both the electronic structure and the nature of the nuclei in the same way. So, and this again exploiting the fact that we can fit an exponential amount of information in our qubits, so we can do both optimization simultaneously. But we are definitely working in that direction. Energy was the starting point, obviously, because you have to get the wave function, right? So the energy is fundamental because it allows you to get the wave function. But once you have the wave function, you can, even the density will be enough, you can access all the properties of the system. So now in the QChem library, we offer at the moment for the public only the energy and the dipole and some other properties that I forgot. And then for the clients, so this is the model, right? There will be two versions, a basic version that is open to the public. And then for the people that are ready to pay a bit, I don't know much, there are other properties available. For instance, the couple cluster approach that we developed, this is separate, and the excited state module is also separate. But as soon as we will progress, this part will become available for the public, and the rest will remain access for the client. So this is the model that we have in mind.
Just one comment. The energy that you're computing is protected because it's a solution of a variational problem. So the energy will be more precise than the wave function. When you apply the wave function to other observables, you are not necessarily as protected as with the energy. That's okay. So let's thank our guests.
I have a question for the room, and I have to make a very small comment. Do we have an engineer in the room? Okay. I understand because we have more than 5% women. No. I am an electronic engineer. We, in electronic engineering, we don't study quantum physics. We don't study numeri primi, the prime numbers, because we have been created for certainties. This is a neo-positive school, yeah. Now, but, and usually in IBM, I am the technical director, I have all the technical people with me. The majority of the people we have in-house are engineers. That is good. It was good in a period of time. What we are doing now, this is just a small information for you. We are moving our new hiring in the space of physicists and mathematician and chemistry. That's the point. And we are opening also new spaces in research in Italy. That's what I am working on. So if some of you is interested, that's a good discussion topic during the buffet. That this was what I wanted to open. Okay. See, being you the only engineer, don't worry, we are two, we can talk together. And by the way, we don't have cats, because we don't know if they are alive or dead. We prefer dogs, and that's okay, but that's good.
Let's thank our speakers, and then we move to the